What do I need to know about other greenhouse gases?
The 20-year global warming potential of methane is 84. That is, over a 20-year period, it traps 84 times more heat per unit mass than carbon dioxide. This is because of the particular vibrational rotational energy state that is activated in the molecule, and because it absorbs in a region where other gases such as carbon dioxide don't absorb. It survives for about 12 years in the atmosphere before reacting with the hydroxyl atom in the troposphere. After a series of reactions, it converts into carbon dioxide. Global methane concentrations have risen by a factor of 2.5, and again it is at the highest value in at least 800,000 years. Its concentration is higher in the northern hemisphere since most sources, both natural and human, are located on land and the northern hemisphere has more land mass. Natural sources of methane include wetlands, which produce 20% of it from bacteria residing in wet soil. Rice fields also act like wetlands. These same bacteria also reside in the digestive tracts of cows and sheep to help them break down plant material. In this way, livestock generates 37% of anthropogenic methane. In landfills, these bacteria take over the decomposition of large amounts of organic material. This contributes 18% of global methane emissions. Methane is a primary component of natural gas, and thus during the production and storage, some of it leaks into the atmosphere. As the Earth warms, there will be a positive feedback effect from the additional release of methane from wetlands and the Arctic permafrost. The story of ozone is interesting. Once there is oxygen in the atmosphere, ozone, another less stable configuration of oxygen atoms, starts building up. This configuration makes the difference between the colorless odorless gas essential for respiration, that is oxygen, and the light blue pungent toxic gas, which nevertheless serves a useful purpose for life on Earth, shielding it from high energy ultraviolet solar radiation. About 5 billion tons of ozone float in the stratosphere, forming a thin protective layer about 50 kilometers above the Earth's surface. High energy UVC light can break the strong bonds of an oxygen molecule. This happens in the atmosphere at altitudes above 100 kilometers, resulting in energetic free oxygen atoms. Lower down, where the atmosphere gets denser, these atoms bind with oxygen molecules to form ozone, which itself can be split by longer wavelength UVB radiation. This cycle continues in the atmosphere. The rates of the reactions depend on conditions in different parts of the atmosphere. In equilibrium, an ozone layer is formed, and thankfully all the UVC and UVB radiation from the sun is used up in the reactions involved. In the 1970s, scientists pointed out that bacteria in the soil produce nitrous oxide, which is also found in fertilizers, sewage treatment plants, nylon production, and is used as an anesthetic, which diffuses upwards through the air, turning into a more reactive nitric oxide and rising as high as the ozone layer, where it too splits ozone. Then there are the chlorofluorocarbons, the CFCs, made up of carbon, chlorine, and fluorine atoms. These are highly non-reactive and have various applications in industry. These too reach the upper reaches of the atmosphere in about 50 years. There they break up in the presence of UV radiation. Each resulting chlorine atom splits up to 100,000 ozone molecules before itself reacting with something and drifting back down. Scientists brought this to the attention of the public, arguing that waiting for further empirical proof was not an option as the threat of ozone depletion was too serious and the release of CFCs must be stopped. Then they stumbled upon the ozone hole over the Antarctic in 1975. Ice-laden clouds over the Antarctic in winter were found to provide a resting place for the descending chlorine molecules. As soon as sunlight fell on them again, they once again began destroying ozone. This finding further invigorated the international response and helped limit the use of CFCs. Ironically, the process that leads to the polar ozone hole will help reduce the effects of global warming because ozone is a greenhouse gas, so depleting it will shield the polar regions from warming too much. Despite this, the release of ozone-depleting CFCs had to be stopped. The point of the story is to highlight that an environmental calamity was avoided through cooperation. A Nobel Prize was given to the scientists for highlighting the role of CFCs. Nitrous oxide is now the more potent ozone-depleting gas, and it is also a greenhouse gas. Nitric oxide is also produced directly by jet engines and supersonic aircraft.